What is plasma? The fourth state of matter. Close your eyes and imagine the sun, that warm light touching your face, traveling 93 million miles through the darkness of space, is actually plasma, the most common state of matter in the universe, yet one you might know the least about. While you learned in school about solids, liquids, and gases, there exists a fourth state, one that fills the cosmos and dances in the sky during thunderstorms. Tonight, let's explore this mysterious, glowing state of matter together, gently discovering the science that surrounds us in ways we rarely notice. Think about ice for a moment. Solid, hard, structured. Now imagine that ice melting into water, liquid and flowing. Heat that water further, and it becomes steam, a gas that rises and disperses into the air. But what happens if you keep going? What if you add even more energy to that gas? Something remarkable occurs. The gas transforms into plasma, a state where atoms themselves begin to break apart, where electrons escape their atomic bonds, creating a soup of charged particles that glow and flow in ways unlike anything else in nature. Plasma is matter that has become so energized that electrons are stripped away from their parent atoms. Imagine a crowd of people holding hands, walking together in an organized group. That's like atoms in their normal state, with electrons orbiting peacefully around their nuclei. Now imagine that crowd getting so excited, so energized, that people start letting go of each other's hands, dancing freely, moving independently. That's plasma. The electrons break free, and what remains is a mixture of positively charged ions and negatively charged electrons, all moving in a chaotic but beautiful dance. This separation of charges gives plasma unique properties. Unlike the air around you, which doesn't conduct electricity well, plasma is an excellent conductor. Those free electrons can carry electrical current easily. Plasma also responds to magnetic fields in fascinating ways, bending and flowing along magnetic field lines like iron filings arranging themselves around a magnet. And perhaps most noticeably, plasma glows. Those excited electrons, when they recombine with ions or drop to lower energy levels, release energy as light. That's why stars shine, why neon signs glow, why lightning illuminates the night sky. You might wonder why you don't encounter plasma more often in daily life here on Earth. The answer is simple. Plasma requires energy, usually in the form of heat, to maintain itself. Here on our planet's surface, temperatures are generally too cool for matter to exist naturally as plasma for long periods. When lightning strikes, it creates plasma for a brief, brilliant moment, heating the air to temperatures hotter than the surface of the sun. But that plasma quickly cools, returning to ordinary air. Earth's atmosphere, thankfully, provides a protective blanket that keeps temperatures moderate, comfortable for life, but too cool for sustained plasma. Yet venture beyond our atmosphere, beyond our planet's protective embrace, and plasma dominates. The sun, that brilliant orb that lights our days, is a massive sphere of plasma, where temperatures reach millions of degrees in the core and thousands of degrees at the surface. The solar wind, a stream of charged particles flowing outward from the sun, is plasma traveling through space at hundreds of miles per second. The space between stars isn't empty vacuum, but is filled with thin plasma. remnants of ancient stellar explosions and the ongoing life cycles of stars. Even the stars you see twinkling in the night sky are distant balls of plasma, each one a nuclear furnace where hydrogen fuses into helium, releasing tremendous energy that has traveled for years, decades, sometimes thousands of years to reach your eyes tonight. When you look up at the night sky, you're seeing plasma everywhere, just very, very far away. Scientists estimate that 99% of the visible matter in the universe exists. We live on a tiny island of solid and liquid matter in a cosmic ocean of plasma. The study of plasma physics is relatively young compared to other branches of science. While humans have observed plasma for as long as we've watched lightning and stars, we didn't understand what we were seeing until the 20th century. The term plasma in this context was first used by Irving Langmuir in 1928, who thought the way electrons and ions moved reminded him of blood plasma carrying particles through the body. It was an apt metaphor, this image of charged particles flowing and moving together. Though the resemblance is purely poetic rather than scientific, understanding plasma required understanding atomic structure, which itself is a relatively recent achievement in human history. Only once scientists realized that atoms consisted of nuclei and electrons could they begin to comprehend what happens when those electrons are stripped away. This understanding opened doors to countless technologies and deepened our comprehension of the universe we inhabit today. Plasma research continues at universities and laboratories around the world. Scientists study how to control plasma for fusion energy, hoping to recreate the sun's power-generating process here on Earth. Engineers develop new plasma-based technologies for manufacturing, medicine, and space exploration. Astrophysicists use plasma physics to understand phenomena ranging from solar flares to the jets of material shooting from black holes. This fourth state of matter, once mysterious and unexplained, now stands at the frontier of human knowledge and innovation. As you settle deeper into comfort tonight, consider this: you are made of matter that once existed as plasma. Every atom in your body was forged inside a star in plasma conditions of unimaginable temperature and pressure. Those atoms were scattered through space when that star died, perhaps in a violent supernova explosion, itself a plasma phenomenon. Those atoms drifted through the plasma-filled space between stars, eventually condensing into the cloud that formed our solar system, our sun, our Earth, and ultimately, you. You are stardust, quite literally. And that stardust remembers its plasma origins in the nuclear hearts of long-dead stars. If you're enjoying this journey through plasma, consider subscribing for more calming science content to help you drift off to sleep. There's so much more to explore, so many gentle discoveries waiting in the worlds of physics, astronomy, and the natural sciences. But for now, let's continue our plasma journey together, moving from these fundamental principles to the spectacular displays of plasma throughout the cosmos. Plasma in the cosmos, stars, nebulae, and spaces, we drift further from Earth. Let's explore the plasma that fills the vast darkness of space, transforming the cosmic void into a luminous tapestry of light and energy. When you look up at the night sky, you're witnessing the largest plasma show in existence. a performance that has been running for billions of years and will continue for billions more. Our Sun, the closest star to Earth, serves as the perfect example of a stellar plasma furnace. At its core, temperatures reach 15 million degrees Celsius, hot enough that hydrogen nuclei overcome their natural repulsion and fuse together, forming helium and releasing tremendous energy in the process. This energy works its way outward through layers of plasma, taking thousands of years to travel from the core to the surface. The surface itself, what we see as the brilliant solar disk, maintains temperatures around 5,500 degrees Celsius, cooler than the core, but still hot enough to vaporize any known material instantly. The Sun's atmosphere extends far beyond its visible surface. The chromosphere, a layer of plasma a few thousand kilometers thick, glows with a reddish hue that becomes visible during solar eclipses. Above that lies the corona, the Sun's outer atmosphere, a region of extremely hot but very thin plasma that extends millions of kilometers into space. Paradoxically, the corona is actually hotter than the Sun's surface, reaching temperatures of 1 to 3 million degrees Celsius. Scientists are still working to fully understand why the corona is so much hotter than the surface below it. Though magnetic fields clearly play a crucial role in heating this outer plasma layer, the Sun constantly releases plasma into space through the solar wind. This stream of charged particles, mostly electrons and protons, flows outward at speeds ranging from 300 to 800 kilometers per second. The solar wind isn't uniform. It varies in density and speed depending on conditions on the Sun's surface. Fast solar wind typically originates from coronal holes, areas where the Sun's magnetic field lines open into space, allowing plasma to escape more easily. Slow solar wind comes from regions near the Sun's equator, where magnetic field structures are more complex. This solar wind creates a bubble around our solar system called the heliosphere, a region of space dominated by plasma and magnetic fields from the Sun. The heliosphere extends far beyond the orbits of the planets, reaching out past Pluto into the realm of the Kuiper Belt and beyond. At its boundary, called the heliopause, the solar wind finally meets the interstellar medium, the thin plasma that fills the space between stars. The Voyager 1 spacecraft crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. Moving from the Sun's plasma domain into the galaxy's plasma ocean, every star you see at night is another plasma sphere, each with its own character and life story. Some stars are cooler and redder than our Sun, their surfaces simmering at 3,000 degrees or so. Others burn blue-white, their surfaces reaching 30,000 degrees or more, radiating tremendous energy into space. The largest stars live fast and die young, burning through their fuel in mere millions of years before exploding as supernova. The smallest stars, red dwarfs, burn so slowly and efficiently that they can shine for trillions of years, far longer than the current age of the universe. Between the stars lies the interstellar medium, space filled with very thin plasma and neutral gas. This isn't empty void, but rather a tenuous ocean of matter, averaging about 1 atom per cubic centimeter. In some regions, the interstellar medium is even thinner, while in others, it condenses into clouds where densities might reach thousands or even millions of particles per cubic centimeter. These denser regions are where new stars are born, where gravity slowly compresses the plasma and gas until temperatures and pressures rise high enough to ignite nuclear fusion. Nebulae, those colorful clouds visible through telescopes, are regions where plasma glows with particular brilliance. Some nebulae, called emission nebulae, shine because nearby hot stars pump energy into the surrounding plasma, causing it to glow in characteristic colors. Hydrogen emits red light, oxygen produces greenish hues, and other elements contribute their own spectral signatures, creating the stunning color palettes seen in images from telescopes. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is an emission nebula where thousands of stars are currently forming, their radiation illuminating the surrounding plasma clouds. Other nebulae represent the death rather than birth of stars. Planetary nebulae, despite their misleading name, have nothing to do with planets. They're shells of plasma expelled by dying stars, glowing as the star's remaining core radiates intense ultraviolet light into the expanding gas. The Ring Nebula, the Cat's Eye Nebula, the Helix Nebula, these beautiful structures are tombstones of stars, their final gasps made visible as glowing plasma sculptures in space. In a few billion years, our own sun will create such a nebula, puffing off its outer layers and leaving behind a small, dense white dwarf core. Supernova remnants represent even more violent plasma phenomena. When massive stars explode, they don't just brighten and fade quietly. They blast their outer layers into space at tremendous speeds, creating shock waves that heat the surrounding interstellar medium to millions of degrees. The Crab Nebula, remnant of a supernova observed by Chinese astronomers in 1054 AD, still glows brightly nearly 1,000 years later. At its center, a rapidly spinning neutron star, the crushed core of the original star, powers the expanding plasma cloud with beams of radiation and particles. Even the space within our own solar system hosts remarkable plasma phenomena. The magnetospheres of planets with magnetic fields, like Earth and Jupiter, create protective bubbles where the solar wind is deflected around the planet. Jupiter's magnetosphere is enormous, extending millions of kilometers into space, and it traps intense radiation belts of high-energy plasma particles. If humans could see these radiation belts, Jupiter would appear larger than the full moon in Earth's sky, despite being so much farther away. The moons of Jupiter experience plasma effects as well. Io, the most volcanically active body in the solar system, constantly pumps sulfur and oxygen into space through its volcanic eruptions. These atoms become ionized, forming a plasma torus, a donut-shaped ring of glowing plasma that orbits Jupiter along Io's orbital path. Jupiter's rapid rotation and strong magnetic field whip this plasma around, creating powerful electrical currents that flow between Jupiter and Io, generating auroras on Jupiter's poles. Those icy wanderers from the outer solar system develop plasma tails when they approach the sun. The comet's nucleus, a dirty snowball of ice and rock, begins to sublimate as solar heating increases. The released gas becomes ionized by solar ultraviolet radiation and the solar wind, forming a glowing plasma tail that always points away from the sun, regardless of the comet's direction of travel. Some comets develop two distinct tails, a bluish plasma tail blown directly away from the sun by the solar wind, and a yellowish dust tail that curves gently, following the comet's orbit. What's your favorite cosmic phenomenon? Leave a comment and let me know what space topics help you relax. As we've seen, the cosmos is fundamentally a plasma universe, with these charged, glowing particles forming the substance of stars, filling the space between them and creating spectacular displays throughout the heavens. But plasma isn't only distant and cosmic. As we'll explore next, Earth itself hosts beautiful plasma phenomena that you may have witnessed, bringing the fourth state of matter closer to home. Plasma on Earth, lightning, auroras, and natural phenomena. While most plasma exists far in space, you've probably witnessed it closer than you think. Perhaps during a thunderstorm's brilliant display, or if you've been fortunate enough to see auroras dancing across the polar skies. Earth, despite its relatively cool surface, creates plasma in spectacular, natural phenomena that have inspired awe and wonder throughout human history. Lightning represents the most common and dramatic plasma event most people experience. During a thunderstorm, ice crystals and water droplets within the cloud collide, transferring electrical charges between them. Lighter ice crystals, carried upward by convection currents, become positively charged, while heavier particles sink, carrying negative charge toward the cloud's bottom. This charge separation builds enormous electrical potential differences, sometimes reaching hundreds of millions of volts between the cloud base and the ground below. When the electrical field becomes strong enough, it overcomes the air's natural resistance to conducting electricity. A stepped leader, a channel of ionized air, begins reaching down from the cloud in a zigzag pattern, branching as it seeks the path of least resistance toward the ground. This initial leader moves relatively slowly, perhaps 100 kilometers per second, invisible to the human eye. As it approaches the ground, the strong electrical field near the surface causes streamers of ionized air to reach upward from tall objects like trees, buildings, or even people. When the downward leader connects with an upward streamer, a complete conducting path of plasma suddenly exists between cloud and ground. In that instant, a massive current flows upward along this channel in what we see as the brilliant return stroke. The air in this channel, typically about 2 to 3 centimeters in diameter, is heated to approximately 30,000 degrees Celsius, about 5 times hotter than the sun's surface. This intense heating causes the air to expand explosively, creating the shock wave we hear as thunder. The lightning channel is genuine plasma, with air molecules stripped of their electrons by the intense energy. This plasma glows brilliantly, radiating light across the visible spectrum and beyond, from radio waves through visible light to X-ray. The plasma channel typically lasts only a few 10,000ths of a second, cooling rapidly as the current decreases. However, many lightning strikes consist of multiple strokes following the same channel in rapid succession, making the flash appear to flicker. Lightning comes in many varieties beyond the common cloud-to-ground strikes. Intracloud lightning occurs entirely within a single cloud, accounting for the majority of all lightning discharges. Sheet lightning illuminates entire cloud sections from within, diffused by water droplets and ice crystals. Cloud cloud-to-cloud lightning arcs between separate thunderstorm cells. Positive lightning, originating from the cloud's upper positive region, is less common but typically more powerful than negative strikes, sometimes carrying currents exceeding 300,000 amperes. Some lightning phenomena are stranger still. Ball lightning, spheres of glowing plasma that float through the air, has been reported for centuries but remains poorly understood. Witnesses describe luminous balls ranging from a few centimeters to several meters in diameter, persisting for seconds or even minutes, sometimes passing through windows or walls before disappearing. Scientists debate ball lightning's exact nature and formation mechanism, though most agree it involves some form of plasma phenomenon. High-altitude lightning events, discovered only in recent decades, occur above thunderstorms rather than below them. Sprites are large red plasma discharges extending upward from storm tops toward the edge of space, sometimes reaching 50 or more kilometers in altitude. They appear for only a few milliseconds, branching like jellyfish tentacles or carrots. Blue jets shoot upward from storm tops at speeds up to 100 kilometers per second, forming narrow cones of blue plasma. ELVs are expanding rings of faint plasma emission in the ionosphere, caused by electromagnetic pulses from powerful lightning below. Auroras, the northern and southern lights, create Earth's most beautiful plasma displays. These luminous curtains, arcs, and rays dancing across polar skies result from solar wind plasma interacting with Earth's magnetic field and atmosphere. The process begins millions of kilometers away, where Earth's magnetic field intercepts the solar wind, deflecting most of these charged particles around the planet. However, some solar wind particles become trapped in Earth's magnetosphere, stored in regions called the Van Allen radiation belts during geomagnetic storms. When the solar wind intensifies, or when magnetic field structures in the solar wind interact with Earth's field, these trapped particles are accelerated toward Earth's poles, guided along magnetic field lines like beads sliding down strings. As these energetic electrons and protons enter the upper atmosphere, typically at altitudes between 100 and 300 kilometers, they collide with atmospheric oxygen and nitrogen atoms. These collisions transfer energy to the atmospheric atoms, exciting their electrons to higher energy levels. When those electrons drop back to lower energy levels, they release energy as light, creating the aurora's glow. Oxygen atoms emit green light, the most common aurora color, from altitudes around 100 to 200 kilometers. Higher altitude oxygen, above 200 kilometers, produces red emissions. Nitrogen contributes blue and purple hues, particularly at lower edges of the aurora curtain. The specific colors and patterns depend on which gases are excited at what altitudes and with what energy. Auroras are genuinely plasma phenomena because the upper atmosphere in these regions becomes partially ionized by the incoming particles. This ionized region, called the ionosphere, is a layer of plasma that surrounds Earth at altitudes from about 60 to 1,000 kilometers. During strong auroras, the ionosphere becomes more densely ionized, affecting radio wave propagation and creating beautiful visual displays simultaneously. The aurora borealis and aurora australis mirror each other at opposite poles because the magnetic field lines guide particles to both northern and southern polar regions simultaneously. Astronauts aboard the International Space Station sometimes orbit directly through the aurora, seeing green and red glows surrounding them in all directions, a perspective impossible from Earth's surface. St. Elmo's fire, another atmospheric plasma phenomenon, appears as a blue or violet glow on pointed objects during thunderstorms or in charged atmospheric conditions. Sailors on ships' masts, aircraft wings, church steeples, and mountain peaks can all exhibit this eerie luminescence. The strong electrical field near these pointed objects ionizes the surrounding air, creating a small region of plasma that glows as charges flow between the object and the atmosphere. Unlike lightning, St. Elmo's fire is continuous and relatively gentle, though it indicates strong electrical fields nearby. Volcanic lightning, also called dirty thunderstorms, occurs when volcanic ash particles ejected during eruptions collide, generating electrical charges through friction. These charges can separate sufficiently to create lightning within the ash plume or between the plume and the ground. Photographs of volcanic eruptions often capture spectacular lightning displays threading through the ash clouds, plasma cutting through the darkness with brilliant orange and purple hues, reflected by the surrounding particles. Even forest fires can generate their own plasma phenomena. Intense fires create powerful updrafts that can develop into pyrocumulus clouds, thunderstorm-like structures formed by fire's heat rather than typical weather processes. These fire-generated storms sometimes produce lightning, creating the dangerous possibility of new fires being sparked by the fire's own plasma discharges. Have you ever seen the northern lights or witnessed a powerful lightning storm? Share your experience in the comments below. These terrestrial plasma phenomena remind us that the fourth state of matter isn't only distant and cosmic. It appears here on Earth, illuminating our skies with natural beauty and power, connecting us to the same physical processes that fill the universe beyond our atmosphere. Yet humans haven't merely observed plasma. We've learned to harness it, creating technologies that bring plasma into our daily lives in ways both obvious and subtle. Plasma in technology. From neon signs to plasma TV, every time you pass a glowing neon sign or turn on certain lights, you're witnessing plasma at work, though you might not realize it. Humans have harnessed the fourth state of matter for countless practical applications, transforming plasma from a cosmic curiosity into an everyday technology that illuminates cities, cleans surfaces, and enables modern manufacturing. Neon signs represent one of the oldest and most recognizable plasma technologies. The basic principle is beautifully simple: a glass tube filled with low-pressure gas, with electrodes sealed at each end. When high voltage is applied between the electrodes, the gas becomes ionized, forming plasma that emits light. The color depends on which gas fills the tube. True neon gas produces the classic orange-red glow seen in vintage neon signs. Argon creates a pale lavender blue. Helium produces a peachy color. Krypton glows white. Xenon emits a pale blue. Sign makers combine different gases and add small amounts of mercury vapor to create a broader color palette. They also use colored glass tubes and phosphor coatings that fluoresce when struck by ultraviolet light from the plasma. expanding the available colors to include bright reds, greens, blues, and yellows. Walking through a city at night, those glowing signs overhead are all small-scale plasma reactors. Their distinctive warm glow impossible to perfectly replicate with LED technology, which is why neon signs retain their aesthetic appeal despite being energy-intensive. The creation of neon signs is genuine craftsmanship. Glass tubes are heated and bent by hand into letters or designs, a skilled process requiring years of practice to master. The tubes are evacuated to remove air, then filled with the chosen gas at very low pressure, typically around 1% of atmospheric pressure. This low pressure is crucial because it allows the electrons to accelerate between collisions, gaining sufficient energy to ionize gas atoms when they do collide, sustaining the plasma. Fluorescent lights operate on similar principles, but with different engineering priorities. A fluorescent tube contains low-pressure mercury vapor. When electricity flows through the tube, the mercury plasma emits primarily ultraviolet light, invisible to human eyes. The tube's inner surface is coated with phosphor compounds that absorb this ultraviolet radiation and re-emit it as visible light. Different phosphor mixtures produce different color temperatures, from warm white resembling incandescent bulbs to cool white preferred. In offices and workshops, fluorescent lighting is significantly more energy efficient than incandescent bulbs because it converts a higher percentage of electrical energy into visible light rather than waste heat. An incandescent bulb is essentially a tiny heater that happens to produce light, whereas a fluorescent tube is a controlled plasma device. This efficiency advantage has made fluorescent lighting standard in commercial and industrial settings for decades. Though LED technology now offers even better efficiency, compact fluorescent lamps, or CFLs, brought plasma lighting into home settings by folding the fluorescent tube into a compact shape that fits standard light sockets. These bulbs use the same mercury plasma principle as linear tubes, but in a much smaller package. The electronic ballast necessary to start and maintain the plasma discharge is integrated into the bulb's base. While CFLs represented a significant improvement over incandescent bulbs, they've largely been superseded by LEDs, which contain no mercury and offer even better efficiency and lifetime. Plasma televisions, popular in the early 2000s, contained millions of tiny cells, each functioning as a miniature fluorescent light. Each cell, called a pixel, was filled with xenon and neon gas mixture. When voltage was applied, the gas ionized into plasma, emitting ultraviolet light that struck phosphors coating the cell walls. 3 subpixels per pixel, with red, green, and blue phosphors, combined to create full-color images. Plasma TVs could produce deep blacks and vibrant colors because each pixel could be completely turned off. Unlike LCD screens, which require backlighting, however, plasma displays had disadvantages. They consumed significant power, generated considerable heat, and could suffer from burn-in if static images were displayed too long. LCD and later old technologies eventually displaced plasma TVs from the market. But during their peak, millions of homes contained panels with millions of tiny plasma cells, creating moving images through orchestrated plasma discharges. Plasma cutting represents industrial plasma application at its most powerful. A plasma cutter forces compressed air or inert gas through a narrow nozzle while applying high voltage. This creates an extremely hot, highly focused plasma jet. This plasma jet can cut through electrically conductive materials like steel, aluminum, and copper with remarkable precision. The plasma both melts the metal and blows the molten material away with its high-velocity flow, creating clean, precise cuts. Plasma cutters have revolutionized metal fabrication, enabling precise cutting of thick materials at speeds impossible with traditional mechanical saws. A skilled operator with a modern computerized plasma cutting table can produce intricate designs from sheet metal, cutting curves and angles with accuracy measured in millimeters. The plasma's heat-affected zone is relatively narrow, minimizing warping and material damage adjacent to the cut. Plasma spraying and thermal spraying use similar principles for coating surfaces. Material in powder form is injected into a plasma jet, where it melts rapidly before being sprayed onto a surface. As the molten droplets strike the surface, they flatten and solidify, building up a coating layer by layer. This technique can apply hard, wear-resistant coatings to engine parts, biocompatible coatings to medical implants, or thermal barrier coatings to turbine blades. The extremely high plasma temperature allows melting of materials with very high melting points, enabling coatings that would be impossible with other techniques. Plasma etching has become essential in semiconductor manufacturing. Creating integrated circuits requires removing material from silicon wafers in precise patterns. Plasma etching uses reactive gases that, when ionized into plasma, chemically react with the wafer material. By carefully controlling the plasma chemistry and energy, manufacturers can etch features smaller than a human hair's width, creating the billions of transistors in modern computer chips. Without plasma etching, the computer revolution would have been impossible. Plasma sterilization offers a gentle alternative to heat or chemical sterilization for medical instruments. Many surgical instruments contain heat-sensitive materials or electronics that would be damaged by autoclave sterilization. Low-temperature plasma, often using hydrogen peroxide vapor, can sterilize these instruments effectively without high temperatures. The plasma's reactive species, including free radicals and ultraviolet radiation, destroy bacteria, viruses, and spores while leaving the instruments undamaged. Even streetlights increasingly use plasma technology. High-intensity discharge lamps, including sodium vapor and metal halide lights. Sodium vapor lamps produce the characteristic yellow-orange glow seen lighting many highways and parking lots. Metal halide lamps, containing various metal compounds, produce whiter light more suitable for sports facilities and outdoor areas where color rendering matters. These lamps are more efficient than incandescent lights and have longer lifetimes, though like other plasma lighting, they're gradually being replaced by LED alternatives. Plasma speakers represent a novel audio technology where sound is generated not by vibrating membranes, but by modulating plasma arcs. By varying the electrical current through a plasma arc, the arc's thermal expansion and contraction creates pressure waves we hear as sound. Plasma speakers produce sound with extremely low distortion across a wide frequency range, though they're typically inefficient and generate ozone, limiting their practical applications. If you're finding this relaxing and educational, Don't forget to subscribe for more science content designed for peaceful sleep. From the gentle glow of neon signs to the focused power of plasma cutters, humans have found countless ways to harness the fourth state of matter for practical purposes. Yet technology represents only one domain where plasma serves human needs. As we'll discover next, plasma is increasingly finding applications in medicine and research, offering potential solutions to some of humanity's greatest challenges. Plasma in medicine and research, healing and discovery, beyond light and spectacle. Plasma holds remarkable promise for healing and powering our future. As researchers worldwide explore medical applications and physicists work toward harnessing fusion energy, these endeavors represent humanity's growing understanding of plasma, moving from mere observation and basic application toward sophisticated control and therapeutic use. Plasma medicine, an emerging field, explores how low-temperature plasmas can treat medical conditions without damaging healthy tissue. Unlike the extremely hot plasmas in stars or fusion reactors, these medical plasmas operate at near-room temperature, remaining safe for direct application to skin and tissues. Generated by electrical discharges in air or other gases at atmospheric pressure. These cold plasmas produce a complex mixture of ions, electrons, reactive molecules, and ultraviolet radiation that can interact beneficially with biological tissues. Wound healing represents one promising application. Studies show that brief exposure to cold plasma can accelerate healing of chronic wounds that resist conventional treatment. Diabetic ulcers, which often heal poorly and risk infection, respond particularly well. The plasma appears to work through multiple mechanisms simultaneously, killing bacteria at the wound site, stimulating cell proliferation, promoting blood vessel formation, and modulating inflammation. Patients report minimal discomfort during treatment, typically describing a slight tingling sensation as the plasma contacts their skin. The antimicrobial effects of cold plasma are particularly impressive. The reactive species generated including ozone, nitrogen oxides, and hydroxyl radicals can destroy bacteria, including antibiotic-resistant strains, without the bacterial populations developing resistance as they do with conventional antibiotics. This matters profoundly as antibiotic resistance becomes an increasingly serious global health threat. A treatment that physically disrupts microbial cells rather than relying on chemical interference offers an alternative that bacteria cannot easily evolve to. Evade plasma treatment shows promise against fungal infections as well. Nail fungus, notoriously difficult to treat with topical medications due to the nail's barrier properties, responds to plasma therapy. The reactive species can penetrate the nail to reach the underlying fungal infection, while the plasma's oxidative effects disrupt fungal cell walls. Early clinical trials demonstrate significant improvement in infections that had persisted despite months of conventional treatment. Cancer treatment represents plasma medicine's most ambitious frontier. Researchers have discovered that cold plasma can selectively kill cancer cells while leaving healthy cells relatively unharmed. Cancer cells appear more vulnerable to plasma's oxidative stress, perhaps because they already operate under higher baseline oxidative conditions than normal cells. In laboratory studies, Plasma treatment triggers cancer cell death through multiple pathways, including DNA damage, disruption of cell membranes, and activation of cellular suicide programs called apoptosis. Clinical trials are underway, exploring plasma treatment for various cancers, including skin cancers, where the plasma can be applied directly to tumors. For internal cancers, researchers are investigating plasma-activated liquids water or saline exposed to plasma and then used to treat cells. These liquids retain reactive species that maintain therapeutic effects even after the plasma source is removed, potentially allowing treatment of tumors deep within the body without requiring plasma generators to contact internal tissues directly. Dentistry has embraced plasma applications enthusiastically. Plasma treatment can disinfect root canals more effectively than traditional techniques, reaching into tiny tubules and complex anatomy where bacteria hide. Dental cavities treated with plasma before filling show better bonding and reduced recurrence of decay. Plasma can also treat periodontal disease, killing bacteria in gum pockets without damaging surrounding tissue, and may help regenerate bone lost to gum disease. Skin treatments using plasma are entering cosmetic medicine. Brief plasma exposure stimulates collagen production and skin regeneration, potentially offering wrinkle reduction and skin tightening without the damage caused by some conventional treatments. The plasma induces controlled microdamage that triggers the skin's natural healing responses, encouraging new collagen formation. Early results suggest improvements comparable to laser treatments, but with less discomfort and faster recovery. Beyond medicine, plasma research focuses intensely on nuclear fusion, the process that powers stars. If humans could harness fusion energy on Earth, we would access an essentially limitless, clean energy source. Fusion combines light atomic nuclei, typically isotopes of hydrogen, to form heavier nuclei, releasing enormous energy in the process. The challenge lies in creating and maintaining the conditions, temperatures exceeding 100 million degrees, and sufficient pressure for fusion to occur at useful rates. At such extreme temperatures, matter exists only as plasma. The hydrogen isotopes deuterium and tritium must be heated until their nuclei can overcome mutual electrical repulsion and fuse. This requires plasma temperatures around 10 times hotter than the sun's core. Containing such hot plasma without it touching any material walls presents a monumental engineering challenge. No material can withstand direct contact with 100 million degree plasma without vaporizing instantly. Magnetic confinement represents the leading approach to this challenge. Powerful magnetic fields shape and contain the plasma in specific geometries. Most commonly, the tokamak configuration, a donut-shaped chamber, where twisted magnetic fields keep the plasma suspended without touching the walls. The largest tokamak currently under construction, ITER in southern France, represents a massive international collaboration involving 35 nations. When operational, ITER aims to produce more fusion energy than the energy required to heat and confine the plasma, demonstrating the feasibility of fusion power. Alternative confinement approaches include inertial confinement fusion, where powerful lasers or particle beams compress small fuel pellets to such extreme densities and temperatures that fusion occurs before the pellet can expand. The National Ignition Facility in California uses 192 laser beams, focusing simultaneously on a tiny fuel capsule, compressing it to conditions exceeding those in stellar cores. In December 2022, this facility achieved a historic milestone, producing more fusion energy than the laser energy delivered to the target, demonstrating that laboratory fusion can release net energy. Plasma research extends beyond fusion energy. Understanding space plasmas helps predict space weather, solar flares, coronal mass ejections, and geomagnetic storms that can damage satellites, disrupt communications, and threaten power grids. As humanity relies increasingly on space-based infrastructure, predicting and mitigating space weather impacts becomes crucial. Plasma physicists study the solar wind's interaction with Earth's magnetic field, developing models to forecast geomagnetic storms, much as meteorologists forecast terrestrial weather. Plasma propulsion promises to revolutionize space travel. Ion drives and Hall effect thrusters ionize propellant, creating plasma that is then accelerated by electric and magnetic fields to produce thrust. These engines are far more fuel efficient than chemical rockets, though they produce modest thrust. Several deep space missions have used ion propulsion, including NASA's Dawn spacecraft, which visited the asteroids Vesta and Ceres. Future missions to outer planets and beyond will increasingly rely on plasma propulsion's efficiency. Laboratory plasma research explores fundamental physics questions about turbulence, instabilities, and wave propagation in ionized gases. These studies advance both basic scientific understanding and practical applications. Plasma instabilities that plague fusion reactors also occur in space, and understanding them helps both predict astrophysical phenomena and improve fusion reactor designs. The cross-pollination between different plasma research areas, fusion, energy, space physics, plasma processing, and plasma medicine accelerates progress across all domains. What scientific breakthrough would you most like to see in your lifetime? Let me know in the comments. From healing wounds to powering cities with fusion energy, plasma research spans from the intimately personal to the globally transformative. These applications share a common foundation: growing human understanding of how plasma behaves and how we can control it. To deepen that understanding, let's explore plasma's fundamental properties, the characteristics that make this fourth state of matter so unique and fascinating. The properties and behavior of plasma now that we've seen where plasma appears. Let's gently explore what makes it so unique and fascinating, delving into the properties that distinguish plasma from solids, liquids, and gases. Understanding these characteristics reveals why plasma behaves so differently and why it dominates the universe. Despite being rare on Earth's surface, the most fundamental plasma property is ionization, the separation of electrons from their parent atoms. This creates a soup of charged particles, negatively charged electrons, and positively charged ions. The degree of ionization varies dramatically between different plasmas. Some plasmas are weakly ionized, with perhaps only 1 in a million atoms stripped of electrons, while others are fully ionized, with every atom broken into nuclei and free electrons. Even weakly ionized plasmas exhibit distinctive plasma behavior because those free charges profoundly affect how the material responds to electrical and magnetic fields. Electrical conductivity ranks among plasma's most important properties. The free electrons can move through the plasma, carrying electrical current far more easily than in ordinary gases or liquids. This conductivity varies with plasma density, temperature, and ionization degree. But even weakly ionized plasmas conduct electricity thousands of times better than air at room temperature. This conductivity creates feedback effects. Electrical currents flowing through plasma generate magnetic fields, which in turn affects the plasma's motion and structure, creating complex interactions between electromagnetic fields and plasma flow. Plasma responds dramatically to magnetic fields through a property called magnetohydrodynamic behavior, often abbreviated as MHD. The charged particles in plasma spiral around magnetic field lines, effectively trapped and guided by the fields. Magnetic field lines passing through plasma are sometimes described as being frozen into the plasma moves. It drags the magnetic field with it, and if the magnetic field moves, it pushes the plasma. This frozen-in property explains phenomena ranging from solar flares to the confinement of fusion plasmas in tokamaks. This magnetic behavior creates distinctive plasma structures. In the solar wind, magnetic field lines stretch from the sun out into space, their geometry shaped by the sun's rotation. These field lines can become twisted and tangled, storing magnetic energy that can be explosively released during magnetic reconnection events, solar flares, where field lines break apart and reconnect in different configurations, converting magnetic energy into particle acceleration and heat. Similar reconnection events occur in Earth's magnetosphere, causing auroral displays and geomagnetic disturbances. Plasma supports waves and oscillations impossible in ordinary matter. Langmuir waves, named after plasma physics pioneer Irving Langmuir, involve collective oscillations of electron density. Imagine a region where electrons are briefly pushed together, creating a zone of negative charge. The electrical forces push these electrons back toward equilibrium, but their momentum carries them past equilibrium, creating an oscillation. These electron plasma waves occur at characteristic frequencies determined by the plasma density, and observing these waves allows scientists to measure plasma properties remotely. Ion acoustic waves represent another plasma wave type, where ions oscillate collectively while electrons respond to maintain quasi-neutrality. These waves propagate like sound waves, but through plasma rather than neutral gas, with speeds determined by electron temperature and ion mass. Alpha waves, yet another plasma wave variety, involve oscillations of magnetic field lines with the plasma flowing along them, propagating at speeds determined by magnetic field strength and plasma density. These waves transport energy through stellar atmospheres and the solar wind, playing crucial roles in heating solar plasma and accelerating the solar wind. Plasma can develop complex structures spontaneously through rather than dispersing uniformly. Plasma can form filaments, spirals. Solar granulation, the mottled appearance of the sun's surface, results from plasma convection cells, where hot plasma rises, cools, and sinks in a continuous cycle. Solar prominences, massive loops of plasma arching above the sun's surface, are structured by magnetic fields, with plasma flowing along field lines in configurations that can persist for weeks. Plasma temperature requires careful definition because electrons and ions in plasma can have different temperatures. In some plasmas, particularly those created by electrical discharges at low pressure, electrons are much hotter than ions or neutral atoms. Electron temperatures might reach tens of thousands of degrees, while ions remain near room temperature. This happens because the electric fields accelerate lightweight electrons efficiently, but massive ions gain energy more slowly through collisions. Cold plasma applications in medicine exploit this temperature difference electrons hot enough to create reactive chemistry, but ions and gas cool enough to safely contact living tissue. Quasi-neutrality represents another fundamental plasma property. Despite containing separated charges, plasma maintains nearly equal densities of positive and negative charges overall. If a region develops significant charge imbalance, the resulting electrical forces act rapidly to restore neutrality. The Debye shielding length characterizes how far electrical effects extend in plasma before being shielded by charge rearrangement. In most plasmas, this length is very small micrometers, 2 centimeters, so plasma appears electrically neutral when viewed on larger scales, even though it's composed of separated charges. However, at scales smaller than the Debye length, electrical forces dominate plasma behavior. Charged particles interact collectively with many neighbors, simultaneously, rather than through individual particle collisions as in gases. This collective behavior distinguishes plasma from ordinary gas. In gas, molecules collide pairwise, with each collision involving just 2 molecules. In plasma, each particle responds to electrical and magnetic fields created by thousands or millions of other particles simultaneously, creating intricate collective phenomena. Plasma sheaths form at boundaries where plasma contacts surfaces, whether spacecraft hulls, fusion reactor walls, or electrodes in plasma processing chambers. Near the surface, plasma cannot maintain perfect neutrality, so a thin layer develops where electron and ion densities differ. This sheath region has distinctive electrical properties, typically developing a negative charge that repels electrons while allowing ions to reach the surface. Understanding sheaths is crucial for applications from spacecraft designed to semiconductor fabrication. Plasma instabilities represent one of the field's great challenges. Plasmas can spontaneously develop growing oscillations that disrupt desired configurations. Fusion researchers battle numerous instabilities that can allow hot plasma to escape magnetic confinement. These instabilities arise from the complex interplay of plasma flow, electrical currents, and magnetic fields. Some instabilities grow explosively in milliseconds, disrupting fusion plasma and terminating confinement. Controlling or suppressing these instabilities occupies much of fusion research effort. Plasma turbulence shares characteristics with fluid turbulence, but involves electromagnetic effects absent in ordinary fluids. Turbulent plasma develops eddies and fluctuations across a wide range of scales, from microscopic to macroscopic, with energy cascading between scales through nonlinear interactions. This turbulence affects how heat and particles transport through plasma, critically impacting fusion reactor performance and determining how the solar wind evolves as it flows outward from the sun. Plasma can emit radiation across the entire electromagnetic spectrum. Thermal radiation from hot plasma follows black-body principles, with hotter plasma radiating more energy at shorter wavelengths. Extremely hot fusion plasma radiates X-rays, requiring specialized materials and cooling to handle the radiant heat load. Plasma also produces line radiation at specific wavelengths characteristic of the elements present, allowing spectroscopic identification of plasma composition and temperature. Synchrotron radiation, emitted when charged particles spiral in magnetic fields, produces intense radiation from radio waves to gamma rays. Depending on particle energy and field strength, plasma can also absorb radiation, with absorption depending on wavelength and plasma properties. Dense, cool plasma absorbs ultraviolet and X-ray radiation effectively, which is why the sun's surface appears sharp despite being gaseous. The surface represents the depth where plasma becomes opaque to visible light. Radio waves, conversely, can penetrate plasma or be reflected depending on plasma density and radio frequency, a property exploited for over-the-horizon radar and ionospheric communication. If you're still awake and enjoying this, consider sharing this video with someone who loves falling asleep to science. Plasma's rich properties and complex behaviors make it endlessly fascinating to study and challenging to control. These characteristics explain why plasma fills the universe, why it creates spectacular natural displays, why it enables diverse technologies, and why harnessing it for fusion energy remains difficult. Yet humanity's understanding continues advancing, opening new applications and possibilities. As we'll explore in our final section, the future holds remarkable promise for plasma science and technology. The future of plasma and final reflections as we near the end of our plasma journey. Let's dream about what the future might hold, imagining the possibilities as humanity's understanding of the fourth state of matter deepens and our ability to harness it grows. The coming decades promise transformative advances in plasma science, with applications that could reshape energy production, space exploration, environmental protection, and medicine. Fusion energy stands at the threshold of practical reality. The breakthrough at the National Ignition Facility, achieving net energy gain from fusion, represents a proof of principle that fusion can release more energy than we invest in creating it. While significant engineering challenges remain before fusion power plants generate electricity for homes and businesses, the path forward grows clearer. The ITER tokamak, scheduled to achieve first plasma in the coming years, aims to produce 500 megawatts of fusion power from 50 megawatts of heating power, demonstrating a tenfold energy gain. Beyond it, demonstration fusion power plants are being designed that would actually generate electricity for power grids. These plants would capture fusion energy as heat, using it to boil water and drive turbines just like conventional power plants, but fueled by deuterium extracted from seawater and tritium bred from lithium. The fuel supply is essentially limitless. Earth's oceans contain enough deuterium to power human civilization for millions of years. Fusion produces no long-lived radioactive waste, no greenhouse gases, and cannot undergo runaway reactions or meltdowns. If technical challenges can be overcome, Fusion could provide clean, safe, abundant energy indefinitely. Alternative fusion approaches are being pursued by companies and laboratories worldwide. Some designs use different magnetic confinement geometries than like stellarators with twisted coils creating more complex magnetic fields, or compact fusion reactors using powerful magnets from recent superconductor advances. Inertial fusion companies are developing laser and pulsed power systems that could compress fusion fuel hundreds of times per second, creating a steady stream of micro-explosions to generate power. The diversity of approaches increases the likelihood that practical fusion energy will be achieved, perhaps sooner than many expect. Plasma propulsion will enable a new era of space exploration. Current ion drives, already flying on some missions, will become more powerful and efficient. Variable specific impulse magnetoplasma rockets or Vasimar engines under development could enable much faster trips to Mars, reducing journey times from months to weeks. This acceleration capability would reduce astronaut radiation exposure during interplanetary transit and make crewed Mars missions more feasible. Future deep space missions might use fusion-powered plasma drives, combining fusion energy with plasma propulsion for unprecedented performance. Plasma processing will continue, revolutionizing manufacturing across industries. Semiconductor fabrication already relies heavily on plasma etching and deposition, and as devices shrink to atomic scales, plasma processes will become even more critical. Plasma-enhanced chemical vapor deposition can create thin films with properties impossible through other methods, enabling new solar cell designs, protective coatings, and quantum device fabrication. Atmospheric pressure plasma jets may enable roll-to-roll processing of flexible electronics, printing circuits on plastic substrates as easily as printing newspapers. Environmental applications of plasma are emerging rapidly. Plasma can decompose hazardous pollutants in water and air, breaking down persistent chemicals that resist biological degradation. Industrial facilities might use plasma scrubbers to clean exhaust gases, removing nitrogen oxides, volatile organic compounds, and other pollutants more effectively than existing technologies. Plasma treatment can destroy per- and polyfluoroalkyl substances, or PF, the so-called forever chemicals that contaminate water supplies worldwide, offering remediation where other methods fail. Agricultural applications are being explored where plasma treatment of seeds can enhance germination rates and plant growth while reducing need for chemical pesticides. Plasma-activated water, created by exposing water to cold plasma, shows antimicrobial properties useful for sanitizing produce or irrigation. These applications could reduce agricultural chemical use, benefiting both environmental health and food safety. Plasma medicine will likely expand dramatically. As clinical trials demonstrate safety and efficacy, cold plasma devices may become standard tools in hospitals and clinics. Portable plasma sources could enable wound treatment in field hospitals, remote clinics, or even home care. Cancer treatment protocols might incorporate plasma therapy alongside surgery, chemotherapy, and radiation, offering another weapon against malignancy. Dental practices could routinely use plasma for disinfection and tissue treatment. Plasma-based sterilization might replace chemical sterilants in medical device processing, eliminating toxic chemical handling and residues. Dermatology could embrace plasma treatments more widely for conditions ranging from chronic wounds to skin diseases to cosmetic applications. The ability to stimulate healing and regeneration without significant tissue damage makes plasma attractive for treating conditions that resist conventional therapy. As understanding deepens of how plasma interacts with biological tissues at molecular and cellular levels, treatments can be optimized for specific conditions and patient populations. Advanced plasma diagnostics will enable unprecedented understanding of both laboratory and space plasmas. Improved sensors on spacecraft will map space plasma environments with greater detail, helping predict space weather and protect satellite infrastructure. Earth-based instruments will probe fusion plasmas with higher temporal and spatial resolution, guiding reactor optimization. Computational plasma physics, running on increasingly powerful computers, will simulate plasma behavior with growing accuracy, predicting instabilities and optimizing configurations before physical experiments are conducted. Plasma physics education and public outreach will help more people appreciate this fundamental aspect of our universe. As plasma applications touch daily life more frequently, understanding basic plasma physics becomes more valuable. Science museums might develop plasma exhibits where visitors safely interact with cold plasmas, seeing how magnetic fields shape plasma or creating their own miniature auroras. Educational programs could bring plasma demonstrations into classrooms, inspiring students toward physics and engineering careers. The fundamental science of plasma will continue revealing surprises. Despite decades of research, plasma physics remains rich with unexplained phenomena and unanswered questions. How exactly does magnetic reconnection release energy so explosively? What mechanisms heat stellar coronas to temperatures exceeding surface temperatures? How can we reliably suppress plasma instabilities? What exotic plasma states exist at densities and temperatures beyond current experimental reach? Each answer spawns new questions, driving continued investigation. Plasma astronomy will advance our understanding of cosmic phenomena. Observatories studying plasma processes in solar flares, stellar atmospheres, accretion disks around black holes, and intergalactic space will test plasma physics theories in extreme conditions impossible to recreate in laboratories. These astronomical plasmas exhibit behaviors we can observe but not yet fully explain, providing natural laboratories complementing Earth-based experiments. As you settle into sleep tonight, consider the plasma surrounding you in ways visible and invisible. The sun's plasma, right now, is fusing hydrogen into helium, releasing energy that will reach Earth in about 8 minutes, warming tomorrow's day. The solar wind plasma is streaming past Earth, deflected by our planet's magnetic field, occasionally triggering auroras that dance in polar skies. Stars throughout the galaxy are plasma spheres at various stages of their life cycles, some being born in plasma clouds, others dying in plasma explosions that scatter elements into space where future stars and planets will form. The universe is fundamentally a plasma universe, with this fourth state of matter comprising the vast majority of visible matter. We live on a small island of solid and liquid matter, a temporary condensation of atoms that once were plasma and will be plasma again someday. The iron in your blood, the calcium in your bones, the oxygen you breathe all were forged in stellar plasma furnaces, assembled from simpler elements through fusion reactions, then scattered through space when those stars ended their lives. Plasma connects everything across space and time. The same physics governing lightning in Earth's atmosphere also governs solar flares on the Sun. The same principles enabling fusion in stellar cores drive efforts to harness fusion energy here on Earth. The same plasma waves studied in laboratory experiments also propagate through the solar, wind, and interstellar space. Understanding plasma means understanding the universe in its most common, most energetic, most dynamic state. Perhaps as you drift towards sleep, you might dream of plasma wonders auroras dancing in greens and purples, stars being born in glowing nebulae, fusion reactors powering future cities, or spacecraft sailing through the solar system on plasma jets. These dreams connect you to the same physical processes that have operated since the universe began.
And so we come to the end of tonight's story. Thank you truly for spending this time with me. If you enjoyed this journey through history, please subscribe and turn on notifications so you never miss a new episode. Leave a like if this helped you relax, and share it with anyone who might need a peaceful night's rest. I'd love to hear from you in the comments. What part of Genghis Khan's story stayed with you the most? What would you like to explore in future episodes? Your voice matters here. Now, let go of the day. Let go of everything that doesn't serve you in this moment. The step is quiet, the wind is soft, and sleep is waiting for you, gentle and warm. Good night, dear listener. Rest well, and I'll see you in the next story.